Once again, we can use the analysis polyphase matrix for fast implementation. Remember that the analysis polyphase matrix is given by this matrix here, with the analysis polyphase components given by this equation here. So we have the sum from m going to 0 to infinity. We have this z to the power of minus m here, and here we have this h of k's. The so-called MDCT filter bank has a prototype or a window length of L equals to 2 times capital N, and it's defined with its filter impulse responses in the direct implementation given here for the analysis filters and the synthesis filters. And we see that in both the analysis and the synthesis filter, we have this modulating function with the cosine. We have this factor of 0.5 here, and here we have this factor of square root of 2 divided by capital N here, and we know that n goes from 0 to 2 times capital N minus 1, and k goes from 0 to n minus 1. The resulting analysis polyphase matrices, when we replace here by the polyphase components, and then we will have this polyphase matrix here, and we see that it still is a square matrix and still is invertible, and it's an n by n matrix. And observe that's the h of k. It has the length of 2 times capital N and is more general than the rectangular window. So it's not just 1 and 0. This h of z is composed of first order polynomials, and our goal is to find a good h of n. Fortunately, the MDCT polyphase matrix can be decomposed into a product of simpler metrics, hence easier to invert to obtain perfect reconstruction. So let's now observe the matrix FA and its sparse structure. So we have here this FA matrix, it's real valued, and we observe this diamond shaped form, and it's beneficial for an efficient implementation. So we're decomposing the polyphase matrix into this FA matrix, a delay matrix, and a DCT4 matrix. So the delay matrix is also the inverse of the matrix is the inverse of each entry. The MDCT synthesis polyphase matrix can also be decomposed into a product of matrices, and here we see that we have this delay matrix inverse, so t to the power of minus 1. We have this FS matrix. We also note this diamond shape here, and we need to have a delay for perfect reconstruction. If we use z, that's looking at the future, is non-causal and is not practical, hence we are multiplying with z to the power of minus 1, generating a delay. This is the cause of our signal delay. We can also have a graphical interpretation of the matrix FA, the analysis matrix, and we see that this matrix is folding the upper and lower quarter of the signal into a length n block. So it's the aliasing components. So this matrix is invertible by matrix inversion containing overlap add. And here we see that it's doing this folding this upper and lower quarter of the signal into a length n block. For perfect reconstruction, we see that the DCT matrix T and the delay matrix DZ, they are easily invertible. The system delay results from making the inverse of D of Z causal, one block, and the blocking delay of capital N minus 1 samples. And the folding matrix, the analysis matrix FA, is also invertible with some simple matrix algebra. And we need to pay attention at the determinant of the matrix. And here we see the determinant in the denominator. And then we can make this determinant to a specific value, so we can guarantee that the matrix is invertible. And even more, we can choose a value that the synthesis coefficients, components, are exactly the same as the analysis components in